So I'm Jayke Nguyen. I work with Twin Cloud Package down at UCSD. So we're going to talk about the long-standing problem of the thermal background. Um, my science motivation is really just to do direct imaging of exoplanets, specifically using NERC2 on Keck. M-band specifically is really great for constraining atmospheric models. We get these really great numbers out, CO2, C to O ratio. We can understand distributed chemistry, and the exoplanet atmosphere is a lot better. We can also understand the cloud coverage of the atmospheres better in M-band. And so specifically on the right here, on the 51 area B model spectrum, here is the M-band data point they have for this particular atmospheric model. The errors on this are actually pretty large. It's kind of hard to see, but the actual data point can represent a large range of models with many different, like a large range of atmospheric parameters. And if you minimize the errors on this M-band data point, you can actually constrain your model significantly better. And not only that, cooler planets are also more accessible at longer wavelengths because the SCDs of these atmospheric models tend to peak at longer wavelengths. And I also want to highlight this recent discovery with JWST of EPS-NDB. So this is actually in the southern hemisphere, so we can't observe it Keck, but I want to point out, so we have the JWST data points, and we see that they imaged it in the mid-IR. But over here, there's actually a ground-based measurement set at 4 microns, set an upper limit in 2008, right? So people way back in the day did think about this target. And the thing is, if you look here, this is the M-band range, right? So they're actually missing where the peak of this SCD is. And M-band data would have either possibly discovered it back in 2008, or just had much better constraints on the atmospheric properties of this planet if we had used M-band instead of 4 microns. Just going into the main issues as to why people typically don't choose M-band. So M-band is at 4.55 to 4.8 microns on Keck. The atmospheric window here is actually pretty messy. There's a lot of absorption features due to water vapor. And you're also seeing through some black body emission of the atmosphere itself. And so when we do imaging, this is kind of a sky image, so there's no target, there's no star in the frame. You see this weird background. It's quasi-static. It's definitely not random. It has structure. It changes slowly over time, and it's also highly dependent on atmospheric conditions. And there's not a super clear origin as to where this background comes from. In the bottom right, I also want to point out that NERC2 is having issues in the bottom right here, so that's just a readout error. And so we think, again, that the thermal background is pretty much the sum of, these main components. The terrestrial water vapor, dust on telescope mirrors, or dust on the optics. And again, atmospheric conditions affect these images, and the dome and the optical bench temperature are just never the same as outside. We don't have a perfect system. And so my student, Natasha, has been working on trying to work on the atmospheric part of this thermal background, but I'll mostly be talking about these last two parts in this talk. And so current strategies to mitigate the background are to, when we want to do our exoplanet science in M-band, specifically you want to subtract the background first, and then apply your typical PSF subtractor algorithms to do direct imaging science. But most approaches to dealing with the thermal backgrounds are kind of brute force. They're really just noise minimization techniques. And so the current state of the art is this low-key background subtraction, and then someone iterated on this, did a PCA background subtraction. But essentially, a typical observing strategy for an M-band night is to dither your point source around the frame and do least squares minimization of this noise minimization region, which is so this is a time series. This is successive frames throughout the night. So you take your PSF, you have this noise minimization region, and then you take another frame after moving PSF, and you use these 3 frames to minimize the noise in this frame. So you're evaluating the background you're evaluating the background at a later time to subtract it from the target frame here. And so this is kind of what we started with for our observations. So we did some non-chronographic imaging at ABRIGA earlier this year. Again, so NERC2 was having issues earlier this year, so we ended up not being able to get that much integration time. We just toss out many frames. But importantly, so we did this dither pattern that I showed before. but we also took sky frames in between those dithers, and that'll become important later. And so I was processing the data. This is doing basic data reduction, and we see that if you look, you see the background is varying slowly over time. And so after staring at this movie for like 100 times, we kind of noticed that there's something moving under here, right? There's literally something underneath this moving. And after discussion with many of my peers, and we came to the conclusion that this was actually the D-rotator on the AO bench. So we were actually seeing that moving background underneath was the D-rotator. And so some helpful essays helped me understand exactly what the optical layout of this system was. And NERC2 narrowcam is offset from the optical axis, so that's a translation. And then the K-mirror drive angle is half of the field rotation. So if you do the translation and then that half drive angle rotation, you end up with this movie. And so you can see that you're actually tracking, some of these dust spots throughout the night. And we're tracking our mysterious thermal background signal. And so this is just a stacked frame or median frame of all these frames of the observing sequence throughout the night. And so our current theory is that it's actually just dust on the D-rotator, also known as the K-mirror up here. This is the optical diagram of the Keck AO bench. But we also think this could be imperfections of the optics itself. So maybe scratches or pock marks that are somehow emitting and emitting correct. But the main thing I want to point out here is that the D-rotator is actually very close to the focal plane of the telescope. And so that means that point sources that are present on the D-rotator would be most readily imaged by an imager further down the way. And so how do we minimize this background? Or how do we get rid of this background? And again, we have Loki and PCA, which are again just least squares minimization techniques. And using that method before, we want to construct a set of basis frames that basically encapsulate all the possible background variation in our images. But most importantly, when people have done data reduction with M-band, they haven't taken into account this extra D-rotator signal in Loki and PCA techniques. So again, your standard set of basis is just the science frames itself. You have your noise optimization region that you want to minimize. But to take into account the D-rotator, you do that translation and rotation, and you add that to your D-rotator frames. You do this transformation into the D-rotator reference frame, add that to your basis, and you also add these extra sky frames that we took later in the night. These extra sky frames actually ended up being really important as well because these sky frames, because we took them in between dither positions, match the air mass, temperature, and D-rotator angle at the time of the observation. And so using this new basis, you again just you construct a background subtraction map by combining it you combine a linear combination of these to make a background subtraction map and do the background subtraction on your science image, and then you end up with your nice background subtracted image. And so after doing the background subtraction, you also just do your standard Loki PCA PSF subtraction techniques. And so this is an example of the reduced data that we have. We actually got a non-detection of the planet here. Likely due to limited observation time, 70 minutes of exposure time just not enough to do the kind of deep contrast that we're hoping for. But the improvement that we're seeing, so here's the contrast curves, the 3 sigma contrast curves we're seeing with the black line is no background subtraction at all. The red line is just with the science frames as the basis only. And then the blue line is with the sky, the science frames, and the transformed D-rotator frames. And we see that adding the D-rotator, you actually get pretty significant gains further away from the stars. So you're getting 2 to 4 better background subtraction further away, 2 to 4 times better than 2 to 4 times better contrast than no background subtraction, and 1.4 to 2 times better than just plain background Loki. But I think this highlights the need that we need to try different observing strategies needed to mitigate the D-rotator itself. And my latest idea is to try and not dither at all, actually, and just turn the D-rotator off. which comes with its own slew of issues because then your PSF will be rotating in the frame and it gets a little confusing, but that might have to be worked out later. And so in summary, basically we found that a significant source of thermal emission is the Keck 2 AO bench derotator. But with proper treatment of the systematics, the effects of the derotator can be removed in post-processing. But I do want to emphasize we're actually still not photon noise limited, right? So there's still this extra background, there's the atmospheric background that is not being fully captured. And so cleaning the derotator, I think, is a good solution, but this thing is just going to accumulate dust like throughout its life. So this technique will still be necessary in the long term. And again, the derotator affects all instruments downstream of the AO bench. So specifically scales is going to be in the mid-infrared, and this will have impact. But yeah, that's it. Thank you.